What I'd like to show you in this video is how to find the volume of a solid of revolution if it's revolved around an axis that's not the x or the y-axis, but another line. So here, revolving about an axis that's not a coordinate axis. Find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x is equal to 1 about the line y equal 1. So I've started to graph this. We have our f of x is 2 minus x squared. That's a parabola with its vertex at 0, 2, and it's going down. And then g of x is 1. So remember, g of x is just another name for y. So that's just graphing the line y equal 1. So I have that graphed. And the region enclosed by those curves is this part that I'm shading here. So I'm going to take that, but I'm not revolving it around the x-axis in this problem. I'm actually revolving it around y equal 1. So think about then the part that really is important of the parabola that we're looking at is just that top part and then where it intersects at the line y equal 1. Now, I have to decide how I'm going to go about setting up the integral to find this volume. And remember, if you have the region tight against the axis of revolution throughout the entire interval, then we can use the disk method in order to find that volume, especially if I'm running my subrectangles perpendicular to the axis of revolution. So here the perpendicular to the axis of revolution would give me vertical subrectangles, so that would be dxing it. And this equation is already solved for y equal an expression in x's, as well as this is an expression that's very easy to integrate. So I want to use the disk method on this when I'm going through and finding the integral, and I want to dx it. So remember, by the disk method, our volume is pi times the integral from a to b of r of x quantity squared dx. And I went through this in a other video of why exactly it is that's our volume formula for the disk method. So now we need to figure out what we have for each of these. Well, our integrals, our limits of integration, because I'm dxing it, you want to scan from left to right, and the x at the beginning of the region is at x equal -1, and then it goes until an x value of 1. So we're going to have our volume from -1 to 1, or for our volume is our pi times the definite integral from -1 to 1. And now this capital R of x, that's the radius reaching from the axis of revolution to the curve as you go. But when I think about how I have to set that up, I can't just use the function this time, because if I use the function, that's going from the x-axis all the way to the curve, and I'm only supposed to be going from y equal 1 up to the curve for where the region is revolved around that axis. Well, if f of x equaling 2 minus x squared takes me for the y coordinate from the x-axis up, I really need to take those values as I go, and I need to subtract 1 from it, because that is what we have to subtract to get just the part of the radius that we want throughout. So in our capital R of x in here, this is going to be where we have our y values from the x-axis up minus what we need to adjust for, because we're not revolving around the x-axis. We're revolving around y equal 1. So this is going to be 2 minus x squared minus 1. That's my radius, and that gets squared. So this is done inside the brackets because we're adjusting for the radius to get our capital R of x, and then we're squaring it. So our volume is pi times the integral from -1 to 1 of, this gives me 2 subtract 1, 1 minus x squared dx. So we're going to square the binomial. That's the integral from pi times the integral from -1 to 1 of 1 minus 2x squared plus x to the 4th dx. And now we can go through and find our antiderivative. So the antiderivative of 1 dx is x minus the antiderivative of 2x squared. Well, it's letter base to number power. Add 1 to the exponent and divide by that. So it's minus 2/3 x cubed, and then plus, add 1 to the exponent, divide by that, 1/5 x to the 5th. And I'm evaluating that from -1 to 1. And remember to plug in the top number, the upper limit of integration, minus plug in the lower limit of integration. So it's pi times 1 minus 2/3 times 1 cubed plus 1/5 times 1 to the power 5, and then minus, in parentheses, plug in the -1. So -1 minus 2/3 times -1 cubed plus then 1/5 times -1 to the power 5. So then our volume is pi times, so this will be 1 minus 1 cubed is 1 times -2/3 is minus 2/3, then plus 1/5. And then if we go ahead and just do our powers and then also distribute the -1, minus the -1 is plus 1. -1 cubed is -1. -1 times -2/3 is a positive 2/3, but I'm subtracting that, so that becomes a minus 2/3. And then -1 to the power of 5 is -1 times positive 1/5 is -1/5, but it's minus a -1/5, so that's plus 1/5. And so when we go through and do the arithmetic operations on them, sometimes I like to leave them just like this first and see if when I combine the fractions with common denominators, if something turns into an integer. So I have 1 plus 1 is 2, and then I have minus 2/3 is minus 4/3, and then plus 2/5. And when you go through and you simplify that, you get the volume is 16 pi over 15 cubic units. So you have pi times 16/15 or 16 pi over 15 cubic units for that volume, spinning it around the axis of revolution, y = 1.